This webcast continues in Worksheet 3F, and we're beginning with problem 5. We're going to work several problems which involve uniform acceleration, and all of these problems are going to require using one of the kinematic equations. Remember, the kinematic equations, that's this set of 4 equations, they only apply. You're only allowed to use them when you know that the situation has uniform or constant acceleration. Okay, and because we've spent so much time interpreting graphs that visualize accelerated motion, we're going to solve these problems not only using the equations, but also using the graphs. Now, as we move to more complicated, complex problems, it will be easier to just rely on the kinematic equations, but it is good to see that they're totally consistent with each other, and if you had a detailed enough graph, you should be able to solve all of these problems with a graph just as well. Okay, so let's look at number 5. Here we have a situation with a poorly tuned car that is accelerating. It goes from rest to speed, or to a speed of 28 meters per second in 20 seconds. So let's see here. I'm going to do it graphically first because that's how we've been solving, or we've been using these graphs so much. So let's see here. I need some axes. 28. I think I'm going to have to go up by 3s. So 3, 6, 12. There we go. That should work. Okay. So I know that at time 0, the car is at rest. So the velocity is 0. And at time 20, the speed is 28. So that's here. And so anyway, it's accelerating. I'll assume it's a constant rate of acceleration. And so for every additional second, the velocity is increasing by the same amount. Okay, so the first question here is, what is the average acceleration? And I would find the acceleration as the slope. So the acceleration equals the slope of this velocity versus time graph. And so let's see, I know that this is 20 seconds, 28 meters per second, and this is 0, 0. And so the slope would be 28 minus 0 divided by 20 minus 0. And so that's going to be 1.4 meters per second squared. That's the acceleration based on this graph. And then it says, how far does it travel? So I'm looking for both average acceleration and how far. Well, if I'm going to use this graph to find out how far, I need to find the displacement. And the displacement is going to be the area here between this graph and the x-axis. So I'll just shade that area. And it would be the area of this triangle, which is 1/2 of 20 seconds times 28 meters per second. And that would be 280 meters. Okay, so we have answered both of the questions using this graph. Thankfully, it wasn't a very complex situation to graph. But now let's use the equations. So a good practice is to make a list of the things that you know, and then we'll use those to choose the equation that we're going to use. And so here, I know that the initial velocity is 0 because it told me that the car starts from rest. And I know that the final velocity is 28 meters per second, and I know that the amount of time that it takes to change the velocity is 20 seconds. Okay, and the things that I don't know are acceleration and displacement. So if I take this set of 4 variables, initial and final velocity, elapsed time, and acceleration, I can see that I want to apply the first kinematic equation because I know 3 of those things and I'm looking for the 4th. So VF goes VI plus the, plus, not equals, plus the acceleration times time. And I'm going to solve for acceleration, so that's going to be the change in the velocity divided by time. And that's going to be the same thing that we calculated on the graph. So it is going to be 28 minus 0 over 20 is 1.4 meters per second squared. So using the equation, we got the same answer that we got using the graph. Then I want to know displacement, and I can really use, at this point, any of these other 3 equations that have displacement. But I think that the last equation looks like the easiest mathematically. That says that the displacement is 1/2 the initial plus the final velocity times the elapsed time. And we get 280 meters. Okay. So far so good. We have solved both of these problems using both the kinematic equations and the graph, and we got the same answers. Let's go ahead and look at this next one, number 6. Now, this looks pretty similar. It says at time 0, this car has a speed of 30 meters per second, and after 6 seconds, its speed is 15. Okay, so at 6 seconds, its speed is 15. And it's the same questions that we had before. What is the average acceleration, and how far does the car travel while the speed is changing? And so, I'll make a list of the things I know here. This time we'll do it in the reverse order. Here, my initial velocity is 30 meters per second, and the final velocity is 15. And the time it took for the velocity to change was 6 seconds. I'm looking for the acceleration, and then I'd also like to find the displacement. Okay, so I can use the same equations because I have the same knowns and unknowns. So the average acceleration is final minus initial velocity divided by elapsed time. Here I'm going to get a negative value, right? Because my final velocity is smaller than my initial. So I end up with negative 2.5 meters per second squared. And the displacement should be half of the VI plus VF times delta T. Girls, make a habit of writing these equations before you plug the numbers in. It will really help you learn, start to memorize them. And so I get, let's see, 135 is the 135 meters is the displacement. Let's see if that's what we get from our graph. So the acceleration should be the slope, and so that's going to be the 15 minus 30 over 6. So yes, we're definitely going to get the same answer for the acceleration. But let's look at the displacement. So here is my x-axis. The x-axis is where velocity is 0. And I have to shade all of the area between the graph and the x-axis. So I end up with like a triangle and a rectangle here. And so the displacement is going to be the sum of those areas, area A plus area B. Area A is half of 6, and let's see, what is the height here? It's 30 minus 15, so 15 meters per second. And then B is just a rectangle, so it's just height times width, so that's 15. And let's just see. And good, I got exactly the same answer. So anyway, let's keep going and try to do a couple more here. I'm going to go to the next one, number 7. Now here, a student is dropping a rock from the top of a 30-meter tall building, and we'd like to know how fast the rock is falling just before impact. Okay, so this is a situation, and we will graph it, but first I'd like to solve it with the equations. So I'm going to write down the things that I know. So the student drops the rock from the top of a 30-meter tall building. That's all they're telling me. Now I see a number there, 30 meters. I guess that's how far the rock travels, right? And so that's the displacement, and the rock is falling down. So I think it falls in the negative direction, so I better make that a negative 30 meters. When someone drops something, and that's what this says is drops, the initial velocity is 0, right? It doesn't say that they threw it down. They didn't give it a big initial velocity. They just opened their fingers and let that rock start falling. So the initial velocity is 0. And this is a situation where there is free fall. The rock is in free fall, meaning that the only force acting on the rock is the gravitational force. The rock is so small that we can ignore any drag. And so the acceleration is negative 9.8 meters per second squared. This is important for free fall. So, they're not going to tell me that, but I just have to understand from the context that when something is falling, that I can assume that it's in free fall. And what I'm looking for is the final velocity. Now, these words just before impact are important because remember, those kinematic equations only apply while the acceleration is constant. And once the rock hits the ground, it may bounce. I'm not sure what it will do, but it will no longer be in free fall. And so it will have if it is moving, it will have a different acceleration than it does during the period when it is falling. So that's why they very carefully are asking me the speed just before impact. So just before it hits the ground, while it is still in free fall, while I can still count on that acceleration being constant at negative 9.8, I want to know how fast the rock is. Okay, so with these variables, the 3 that I know and the one that I'm looking for, there's only one equation that I can use, and that's that VF squared equals VI squared plus 2 times the acceleration times the displacement. So here I know everything except for the final velocity. And when I solve this, I'm actually going to have VF squared, right? And so I will have to take the square root to find the final velocity. And when, or as the rock falls, it is moving in the negative direction. And so I have to understand that I'm looking for that negative root, right? So make sure you put the negative on there if you're looking for the velocity, because we understand that that rock is moving down. Now, it is possible to solve and answer these questions using a graph, but it's hard to do. But let me give you a little bit of an idea for that. So here, the rock, the initial velocity is 0, and I don't really know how fast it's going to get, but I'll use the same kind of scale that we've been using. Actually, I know it won't take very long for it to fall, so I think I'll just go ahead and... Okay, so I know that it begins at a velocity of 0, and it falls -30 meters, so we'll end up down here, but I don't know how much time that takes. Well, we have just figured out that the final velocity is going to be -24, and so, but again, I don't know how long it's going to take to fall. I do know that the slope of my velocity versus time graph should be -9.8. And so just for the ease of graphing this, I'm just going to round that to 10. So it starts at 0. After 1 second, the velocity should be about -10. After 2 seconds, it should be about -20. After 3 seconds, it should be -30. So somewhere along this line is the, that's the velocity versus time graph. I'm just not sure how much time it takes for it to fall. I do know that the area between this graph and the x-axis. Now the x-axis is up here where velocity is 0. So this area, I have to find how much time does it take before that area equals -30. And so I would have to do some iteration and maybe like assume, well, what if time was 1 second? And what would that area be? And then what if time was 2 seconds? What would that area be? And so on. So it would be fairly difficult to work your way into the answer, but you could do it. So this is a good example where the equations make it much easier on you. Okay, and let's look at one final problem. I want to look at number 9. Okay, so here we have a car whose initial speed is 30 meters per second and slows down uniformly to 10 meters per second in 5 seconds. So and let's see here, so this would be 6, 12, 18. So at 5 seconds it should be at 10. And since it slowed uniformly, that's a straight line. And the questions are to find the acceleration of the car and then also the distance that it traveled from time 2 to time 3. So let's see here what we know. So I know the initial velocity is 30 meters per second. The final velocity is 10 meters per second. The elapsed time is 5 seconds. So I could pretty easily find the acceleration just from the definition of average acceleration. It would be 10 minus 30, that's final minus initial, over 5 is -4. Okay, and then we want to know the distance, but not the total distance that it's moved while the speed is changing. We only want to know the distance from time 2 to time 3. So I want to know this amount of distance. Now, using the graph, that's not too hard, although I would need to find these points that I've just made little green dots at, because I don't really know what is the velocity at time 2 and what is the velocity at time 3. I could figure that out though, right? Because I could use that first kinematic equation. And so at t equal 2 seconds, the final velocity would be 30 plus -4 times 2. So it would be 30 minus 8 would be 22 meters per second. And at t equal 3 seconds, the velocity would be 30 minus 12, which would be 18 meters per second. So I do know now those green points, and so I could find the area. So the area is the displacement, and it would be the area of this trapezoid, which would be 22 plus 18 times the height is 1 second. And so it would be 20 meters. Okay, but let's see if we could do that using an equation. So I'm going to write, I'm going to use the fact that the displacement is the initial velocity times time plus 1/2 the acceleration times the elapsed time squared. And I think I have the information to use this equation because I know the initial velocity, we calculated the acceleration, I know the elapsed time, and I'm looking for the delta x. So let's see here. So this would be, oh, but I'm looking for the elapsed time being from time 2 to time 3 is 1 second, and the initial velocity is the velocity at time 2, which is 22 meters per second. Because again, I'm trying to just find how far it moves from time 2 to time 3. So my initial velocity has to be the velocity at time 2. Okay, so the displacement would be 22 times that elapsed time plus 1/2 times -4. And we get 20 meters. So again, I get the same thing with the equation, that I would have gotten using the graph.